So let's start our session today. The topic continuing shaft is going to be on shaft design. Okay. Previously, we talked about shaft assemblies in general, kind of, the components that goes on it, why, shaft are very important in machine design, right? We discuss about shaft being the center point of machineries because that's where the power is transmitted. All right, let me do slideshow. Hold on. Okay, let me know when the slide shows up.
Udah, Pak.
There. Okay. Okay, so shaft is at the center point of any machineries because it's just the most practical way to transmit power, right? You need power, let's say in your automotive, right, in a car, to move your car forward. Yang belum nyalain kamera ya. It just helps you focus, it's for you, not for me. The car needs to move forward in a linear way. However, there is no practical way to generate power in a linear way if you think about it, right? Maksudnya, let's say ya kayak pneumatic cylinder, for example, we want to use pneumatic cylinder to move your car. Well, it can only move a certain finite stroke forward, and that's it. And then you have to go back and forth. I mean, that's just impractical. So the more you think about it, rotational power is just much more practical than linear power. I mean, unless you're on a spaceship or pesawat terbang, right? I mean, you shoot air to the back and then you just keep moving forward. I mean, that's linear power. But in most cases on land, you just need it rotational, because in a rotational power you can do this continuously, and the way you do this is through shaft. So here is a typical shaft, right? You put gears on it, or belts, or pulley, or chain, and because you do that, you're going to have steps on the shaft. And this is where we're going to focus our attention, okay? These things are there to keep the elements on location, okay? So a gear, I want the gear to be located here, for example, right? Or here. Now, in order to keep it there, or here's your bearing. Di ujung sini, mungkin ada ball bearing, right? Now, to keep things there, usually there is a shaft shoulder. Okay, this thing is called a shoulder. Because if you look at it vertically, it's like a shoulder, right? I mean, this is your head, it's small, and then there is a bigger shoulder. So these things are called shoulders. It's there to keep an element on location, on a precise location, and then you keep it there. Now, you don't have to have a shoulder, but this is just the most practical way. And the shoulder also keeps you from sliding axially because of some reaction. Kalau kalian lihat ini, ada yang tahu nggak ini namanya apa? What kind of gear is this? Anybody want to make a guess, even though we haven't discussed it?
Spur, Pak.
A spur gear will be straight, and this.
Oh, ini helical ya?
Yes. As you might expect, what is the difference when you have the gear tooth miring dibanding gear toothnya straight? What will be the main difference?
Surface area, Pak.
You increase the surface area, but what does the angle creates in terms of forces?
Ya, kemiringan, Pak. Kayak angle-nya mau apa? Kalau misalnya seandainya di shaft rata yang gak ada shoulder, dia mau miring, Pak.
Right.
Dia mau disengage sendiri.
It will tend to slide, right, along the shaft. because of that angle. And this is called axial reaction. We will study that when we get to gears. So because of these things, you know, you want shaft to be to have shoulders. But as a consequence of the shoulder, the analysis, the stress analysis of shaft is no longer simple. Because previously you can just treat a shaft like a straight rod, right? Remember in strength of materials, kalian ada torsion, gitu kan? Semuanya polos kan shaftnya ya. Tapi in practicality, jarang shaft itu polos. Usually you have these shoulders. What does this shoulder create? This creates what is called a stress concentration. And this might be a new concept, the first new concept that you're learning in this course, right? That, you know, when you, semoga masih ingat ya. When you learn these formulas, bending stress, kalau torsion apa ingat nggak?
TC over J, Pak.
TC over J, good. Okay, these are the maximum torsional shear stress or maximum bending stress, because you're applying load on these geometries. But this is made even worse at these stress concentrations. Okay, what I'm showing to you, the colorful chart is from what is called a finite element analysis. Someday in advanced classes you might learn this. I actually want you to learn this. I think you did this in SolidWorks, right? Belum ya? SolidWorks kalian nggak sampai analysis seperti ini ya, structural analysis?
No, sir.
Enggak ya, cuma gambar-gambar doang ya di technical drawing ya?
Iya, sir.
Yeah, so I actually want you guys to do this. Well, maybe if we have some extra weeks, we might do this. Okay, now if you run this analysis on software, I mean, these kind of software are very advanced. In fact, when you work, especially in developed countries where they do design properly, yeah, you will do this kind of structural analysis, and you will notice that these red dots, the concentration of stresses are often at the shoulders, right? Every time you have an abrupt change, these are kind of the stress flow lines. Kalian lihat garis-garisnya itu ya. Di sini kan ada perubahan yang drastis tuh. Sharp. Ya, every time you have a sharp transition, itu selalu titik failure. Jadi kalau shaft ini bakal fail, more than likely it's gonna fail at this stress concentration. Even though your maximum stress according to MC over I is so and so, it will be multiplied many times over. Oke, di sini kalian lihat aja nih skalanya. Ya. Lihat aja skalanya. Yang biru berapa tuh? 0,671 10 pangkat minus 5 ini deformation I think ya. And yang merah itu 10 pangkat minus 4. Jadi perbedaannya itu 10 kali lipat. You know, we're talking about 10 times over. So the stress concentration becomes very, very important. It becomes literally, I mean, your stress concentration multiplier will be the most crucial failure point or failure consideration. Jadi dibanding MC over I, itu becomes nothing compared to the stress concentration. This will be multiplied 10 times over. Okay? So that's the concept here about stress concentration. This is made worse during change in radius and sharp radius. Okay? Now, it will be made even worse in dynamic loading, but we're not talking about that yet. Okay? Now, we're going to talk about the nature of stress concentration first. Now, the best the most influencing factor is the radius. Jadi kalau kalian gambar ini ya, ini kan ada dikasih radius nih. Oke, dikasih R ya, dikasih fillet. This fillet will reduce the stress concentration. The sharper the fillet, the worse it becomes. Oke, jadi kalian lihat di sini ya, kalau radiusnya 2, 1,35, 1,72, so this radius becomes the biggest influence. So one influence is the ratio between the big D and the small d. The other influence is the radius. Jadi kalau yang tajam, radiusnya kecil atau besar?
Kecil, Pak.
Kecil ya. So as radius decreases, stress concentration factor increases. Okay, as radius decreases, stress concentration increases. And we will see that on the chart that we will about to use. Okay, now there are two types. This is for bending. So when we talk about bending, we talk about KF and KT. And for torsion, it's KFS and KTS. The S here stands for shear. Shear, if you recall, is caused by torsion, right? Torsion creates shear. Shear itu apa sih? Shear itu tuh stres yang sifatnya begini ya. Kalau bending dia stretch, right? Bending stretches, but shear bikin dia tuh menjadi apa ya? Terpotong gitu kan. Kalau saya ada, if I have a bar, okay, if I bend this, yang atasnya terjadi apa? Stretching, right? Jadi atasnya itu mekar gitu kan, memanjang. Tapi kalau saya twist, when I twist a bar, what happens? This is called shear. Ya, begitu. Satu naik, satu turun gitu kan. Bayangin aja kayak tangan kamu dipelintir lah. Oke, kalau tangan kamu dulu waktu SD ya, kadang-kadang suka ngisengin orang dipelintir, diginiin kan, sakit kan. Nah, tapi sakitnya itu apa? Sakitnya itu kan bergeser gitu ya. Oke, shear itu Indonya tegangan geser kalau nggak salah, shear stress. Well, normal stress stretches, so that's why it's normal stress, right? Sigma, MC over I. So KF and KT refers to the bending stress concentration factor, and the KFS, KTS, S stands for shear, represents torsion. We have these two things going on in a shaft typically. So this is a typical table that you will use to determine stress concentration factor. So stress concentration factor is looked up on a table like this. This table is looked up by first D over D. Okay, so the big D divided by the small d. Okay, look at the diagram. I mean the sketch here, right? Large diameter, small diameter. So which one has the worst stress concentration factor? When you have a small change or a large change in diameter?
Large, Pak.
When you have a large change, yeah? So D over D equals 3 is here. D over D around 1 is here, or 1.02. So the more contrast, jadi misalnya shaftnya itu dari besar tiba-tiba jadi kecil, itu mengakibatkan stress concentration yang lebih tinggi, yang lebih buruk. The other one will be R over D, down here below. Okay? So R is the radius of the fillet. Kalau dia sharp corner, perfectly sharp corner, itu berapa radiusnya?
0, Pak.
0, ya. So what happens when the radius is 0? What is the
Ya,
KT?
KT-nya ya tinggi banget, Pak.
Tinggi banget ya, infinity. I mean, maybe like 10 times. Okay, so this is why you always do a radius on a shaft shoulder. Almost always. Something, nggak boleh perfectly sharp. Itu kamu bakal, I mean, it's going to be a failure point in no time. Okay, so you have a radius. Now, this radius then is divided by the small d, and this is the ratio. Okay, R over D. As R over D increases, what happens to the stress concentration? Naik
Ya,
atau
makin
turun?
turun, Pak.
Makin turun ya. So, at a certain point, for example here, you see that around R over D equals 0.15, it's you kind of remove most of the worst effect, right? Your stress concentration factor is already below 1.5 here, right? So kind of a general rule you can say, right? I mean, you want your R over D ratio to be 0.15 or 0.1. Shaft 10 mm, misalnya ini 10 mili, ini 20 mili diameternya. Radius kamu mesti berapa? Kira-kira. Radius fillet kamu ini di sini. Use the chart. Kira-kira paling nggak saya mau remove the worst effect lah. Gampang dong. Ini kan rasio. Jadi ini kan small d. This is the big D. Jadi radiusnya kira-kira berapa?
1,5, Pak.
Ya, kira-kira 1,5 mili ya. And you will be fine. Okay? So this kind of gives you a general idea, right? Of how you would use these things. But we'll use it in actual calculation soon. Another factor is Q. Q is notch sensitivity without going into detail because I kind of skip one module so we can cover more material in this semester. I removed the fatigue failure material, so you just have to kind of catch on here. Okay, Q is notch sensitivity. The way these things fail, waktu kamu ada shaft shoulder, lalu kamu bending, waktu dia fail di sini, dia fail usually due to cracks. Okay? Some imperfection on the surface that then propagates, lalu merembet. Ya, jadi ada retak lalu merembet. That's why we talk about notch sensitivity. Notch sensitivity Q in this chart is affected again by the notch radius. The greater the radius, the sensitivity is less, meaning it's not as bad. Ya, jadi ini kebalik nih. Q, greater Q is actually not meaning that it's not as sensitive. Okay, so let's do an example here. We have a shaft with some shoulders going on and it's under load. Okay. Di sini ada support R1 and R2. Consider them like bearing support. So we have a load vertically 6.8 kilonewton. And so this creates bending, as you can see. we are not going to go through the strength of materials calculation because we will not have time for it. So we will jump into the stress concentration. Now, I can tell you here that M max is not affected by stress concentration, right? Ini dari shear and moment diagram ya. If you recall your strength of materials. Even though the bending moment is maximum at this point, I'm going to call this point E. Even though the maximum moment occurs at point E, they are not subject to stress concentration. But point B, C, well, point D is not this, it's at the outermost, right? Point B and C is subject to shaft shoulder stress concentration. Now, the question becomes, which one of these are worse? Right? Yeah, I'll skip that part too. So, because MB is larger, okay, we can qualitatively evaluate that MB is larger than MC. Stress is MC over I, right? Not the same C, but you know, MY lah. Kita taruh MY aja. Ya. Y itu apa? Ada yang ingat? Kalau shaft is under bending, this is the neutral axis. What is Y? Nggak ada yang ingat? What is I?
Inertia, sir.
Huh?
Inertia.
I is area moment of inertia, right? If it's a box, it's BH cubed over 12, right? And here is pi r to the fourth, if I remember correctly. Now, Y is the distance from the neutral axis to the outer edge, or wherever you are interested in calculating the moment or calculating the bending stress. At maximum, it's on the outside, it will be the radius, okay? So, because MB is larger than MC, I can qualitatively say that the stress at B is greater than the stress at C, correct? But I have to multiply it further with the stress concentration factor. Now, we have to then evaluate not just stress at B and stress at C, but what about their stress after I multiply with the stress concentration factor? You see the shoulder geometry at B and the shoulder geometry at C. Can anyone tell me which one would have a worse KF? Yang mana yang efek stress concentration-nya terburuk? At B or at C? Which one is it?
B bukan, Pak.
Kenapa?
Karena diameter kecilnya cuma 32, sedangkan kalau yang di bagian kanannya diameter kecilnya 35.
Correct. Assuming that the fillet radius is the same, right? The D over D, the big D over D over small d, will be worse at B. Yeah, remember our chart? With a larger ratio, larger contrast, you will end up with a larger KF. So we can then evaluate, we will concentrate at yeah. How do I change the color? Okay, so we will focus at point B. Does everyone understand why we focus at point B? First of all, it's a shaft shoulder, so failure will occur there. And the multiplication from MB will definitely go above Mmax most of the time. So the shaft, even though Mmax occurs right at the loading point 6.8, it's going to fail at MB. All right, it's going to fail at point B. So I don't have enough space. I'm going to erase this. So we're going to do, I need an extra empty slide. Udah kelihatan ya? So I'm gonna cut at B, okay? I'm gonna do a cut at B, and we're going to evaluate the internal moment at B. This is R1, and this is the internal forces, V and M at B. Okay? This is my x-axis going out from the left to the right. So sum of moment at B is equal to MB minus R1 times X equals 0. So MB is equal to R1X. Again, I'm skipping some of these calculation, right? To find R1 and R2, you have to do a sum of moment about D, right? If I do a sum of moment about D, this is counterclockwise is positive, right? So 6.8 kilonewton times, what is that? 100 tambah 125, 225 ya, 0,225. Itu kan counterclockwise ya, positif, minus R1 dikali 250 tambah 75, 100, 125, 225, 75, 300, 550 ya, 0,550 sampai dengan 0. And then you find R1, right? So without doing all that, R1 is 2.782, and X is the distance from A to B, which is 250, yeah? So this is 250. So we find MB is 695.5 Newton meter. So that's the internal moment. Now we're about to find sigma at B. Now we have to multiply KF because that's the stress concentration factor. Okay, so we're gonna do this. But in order to find KF, we need to look up the tables. Okay, MBC over I itu kan masih pelajaran semester 2 ya. What is new here is KF. So I'm trying to build on top of your knowledge that you have previously here. Okay, KF is obtained by this chart. So the first step is to calculate D over D, right? In this case is 38 divided by 32, 1.1875. Okay, I obtained this from the geometry. This is small d, this is big D. We're focusing on the shaft shoulder at B. All right, at point B here, big diameter is 38, small diameter is 32. So D over D is 38 over 32. Did I tell you guys the fillet radius? They don't tell you the fillet radius, but it's given. All right. So fillet radius R divided by small d. That's the second thing that we need. It's going to be 3 divided by 32. Okay. So the fillet radius is 3. Yeah. 0.094. So maybe I should add here in the problem statement fillet radius is 3 millimeters. Here, R equals 3. Ya, jadi shaft shouldernya itu ada lekukan ya, fillet radius. Nah, gitu kan. This is called the fillet radius. Okay, so we have D over D, R over D. Now we are ready to use the chart. D over D is 1.18. Now, this line is 1.5, this line is 1.1. So 1.18 is around that line. Okay, kita kira-kira ya. And then R over D is 0.094. That's approximately 0.1. So our KT here is approximately 1.65. Now this is KT, not KF. So from the chart, KT is equal to 1.65, approximately. The next thing we have to find is Q. Q is the notch sensitivity. The way you look up is from the SUT, which is the ultimate strength. And the material here, SUT, is 690 megapascal. This is an example from the textbook, by the way. So you can always consult the textbook if my problem statement somehow is not clear. Maybe I deleted some of that properties on that problem statement. Okay, so SUT is given. 690. This is a material property. Yeah. And the notch radius is 3. So we follow SUT is 690 MPa, which is approximately, not approximately, in GPa, gigapascal. It's around 0.7, kan? All right, so 0.7 is this line. And notch radius is 3. So here is my notch sensitivity. Q. So Q is approximately here 0.85. Now I understand what you're going to ask. What if we get it different, but in the quiz? It's okay. All right. So this is an approximation using the chart, and it's okay to kind of make a rough estimate. So we obtain our Q. Therefore, my KF, my KF, the formula is 1 plus Q times KT minus 1. So it's 1 plus 0.85 times berapa tadi yang sebelumnya? 1.65 ya. 1.65 minus 1. So we have 1.55. Any questions on finding KF? Okay, so this is my stress concentration factor that I'm going to use here. 1.55, 695.5, 0.016, pi over 4, 0.016 to the fourth. This is your bending stress without stress concentration factor. We now basically multiply by 1.55. Okay. C is 0.16, 0.0616 because we use the smaller diameter. Ya. Jadi MC over I-nya, C-nya atau R-nya kita pakai dari the smaller body of the shoulder. Okay. Its radius, its diameter is 32. So the radius is 16. Okay. So that's why we use 0.016. Everything is in meters, by the way. So we have 1.55 multiplied by 216. And this is 335 MPa, megapascal. Okay, so you can see without the stress concentration factor is 216 would be what you calculate in semester 2. The addition here is the multiplier 1.55. So now the actual bending stress will be 335. It's multiplied 1.55 times. Okay, any questions on this example problem? What we did was we learned how to calculate stress concentration effect in shaft bending. Okay, so the shaft is under bending. What we did was estimating the effect of shaft shoulder at B. Okay, I think I'm losing you guys. You guys still with me?
Masih
Bentar,
Pak.
ya.
All right.
Bisa.
So, yeah. We talked about this. If you want to reduce this effect, then you put some radius. Again, these are some simulation from computers showing you the effect at shoulders or change in radius. Ini kalau ulir drat juga kayak gini nih ya. Ini dari, ya kan, dari drat baut, dratnya baut. Itu di ujungnya, di lembahnya itu, that's where your stress concentration is. Again, that's where it probably will fail. If you bend it until it fails. Every time you put a bearing on, the bearing itself has a radius. Oke, jadi ball bearing itu juga ujungnya agak tajam kan, sengaja karena it allows you to follow that radius. Jadi misalnya ini bearing ya, ini ada bola-bolanya gitu kan. Jadi dalamnya ini nih nggak tajam. It gives you, there is a radius, and so therefore when you fit the bearing on the shaft shoulder, you just follow that radius. You can also add, additional relief groove like this. What happens is that it kind of helps the stress flow lines to be smoother transition. So that kind of helps also if you're under a lot of bending. You can do an undercut like this. That also helps, karena radiusnya jadi lebih besar ya. Ada ruang untuk dia lebih besar. Karena kalau kamu mau bikin radius terlalu besar kan, jadinya kan kayak gini kan. Nggak bisa fit dong. Bearingnya gimana caranya fit? Karena bearingnya kan lebih tajam ujungnya. So, in order to kind of relieve that, you can do that. Okay, so, we're gonna now talk about stress cycling. To add to the harsh effect of stress concentration, now we add stress cycling on top of this. Jadi bukan cuma ada efek shoulder ini, sekarang shoulder ini kena stresnya tuh cycling. Because when you rotate the shaft, yang tadinya di atas jadi di bawah, jadi tension, jadi compression. Compression jadi tension. Jadi bayangin ya, kalau misalnya saya ada kondisi shaft seperti ini, ada load 20. Jadi kan bendingnya kayak gini kan. Nah, saya perbesar tentu saja ya. Jadi karena ada reaction dari bearing di C sama D, kena load seperti ini kan jadi bendingnya begitu ya. Yang tension mana, yang compression mana? Which side is under tension, which side is under compression?
Yang atas tension, Pak.
Okay.
Bawahnya dikompres, jadi lebih kecil.
Now what happens when this axle rotates?
Kebalik, Pak.
Yang tadinya, jadi imagine ya, bayangin kamu semut, okay? Let's say you're an ant and you stick to the top of that shaft. Now when the shaft rotates, when you're at the bottom, suddenly what you experience is compression. Now how often does this happen? This happens very, very fast, right? So let's estimate. For a rotating shaft, 1,200 RPM, which is relatively, medium speed lah. How many stress reversal does this shaft undergo per second? Okay? Kalau shaft ini rotate, dari atas ke bawah ke atas, ya, jadi kan saya cycle nih. Right? If this is positive tension, negative which is compression. Kalau saya berdiri di atas, right? If I'm standing on top, I rotate down and I experience compression. I go back up, tension. So that's one rotation, right? If this shaft rotates 1,200 RPM, how many cycle do I undergo per second?
Itu Pak, 40 Pak. per second, Pak.
1.200 dibagi
Kan 1.200 kan itunya, Pak, roundnya, Pak. Jadi kalau misalnya dalam satu round ada 2 cycle tension compression, artinya dia 2.400 kan, Pak?
per menit.
Iya, per menit, Pak.
Tapi
Dibagi 60 jadi itu, Pak,
ya,
40.
dibagi 60 jadi berapa?
20
ya.
rotation, ya, 20 RPM.
20 revolution per second. Let's say one cycle is from the top down to the top again, gitu aja ya. So one stress cycle meaning going from tension to compression to tension again. Supaya simpel aja. Okay, so that's 20 cycle, right? We can call this cycle per second. Imagine that. In 1 second, kamu tuh di stretch, di compress, di stretch, compress, stretch, compress, stretch, compress 20 times per second. Kemarin kan saya sempat bilang dengan paperclip aja ya. Paperclip kamu gituin aja, nggak lama udah patah kan. So, you are experiencing a lot of fluctuation in stress here, right? Ini baru 20 per detik, 1.200 per menit. Per jam berapa? 1 jam berapa kali cycling? Kali 60, berapa tuh?
72.000.
72,000 cycle per hour. And if this shaft is like an axle on a kereta api, on a train, dan ini baru sejam. Baru sejam ini udah 72 ribu kali di cycle. Let's say it operates 8 hours per day. Kali 8 berapa? 72 kali 8. Ada yang ada kalkulator? Biar bangun, ayo hitung.
576, Pak. 576.000.
576,000 times in 1 day. Kali 30 per bulan. Ya, kalau ini 500.000 berarti berapa tuh? 5 kali 3, 15 juta ya per month. So you can easily see this cycling will have a greater effect than the static loading. In fact, fluctuating stresses will be the controlling failure point or failure effect to failure in most cases rather than static load. Jadi, kalau misalnya kamu static, misalnya in static load, you need 100 tons to fail. In cycling, 20 ton aja kamu bisa fail. Okay? To give you kind of a perspective. If it takes you 100 kilogram to fail something in a static load meaning, you know, ya udah static aja, diam gitu ya, dikasih beban dan diam, seperti building misalnya, diam. Tapi under fluctuating stresses, especially with millions of cycles, you can easily fail far below that. 20 ton itu sudah cukup untuk bikin shaft kamu fail. If it's fluctuating. So that's kind of a summary of what is called by fatigue failure. So this is called fatigue failure versus static failure. In fatigue failure, you don't fail only by the load, but the load fluctuating over however many thousands of cycles. That's called fatigue failure. Dan lucunya begitu ya. Lucunya adalah dengan load yang lebih kecil, tapi cycling, shaft kamu bisa patah. Bukan karena loadnya terlalu besar. Loadnya sih kecil, tapi dia plus minus. Atau plus lalu nol, plus lalu nol. Jadi perbedaannya yang atas, tengah, sama bawah ya. Kalau yang atas itu, dia fluctuating misalnya nih, dari 10 MPa jadi 20 MPa. Oke? Kalau yang bawah ini, yang tengah nih, dari 0 jadi 10 MPa. Kalau yang bawah ini, cyclingnya 10 sama minus 10. But all of them are cycling. Okay, all of them are fluctuating stresses. So this is what we're going to study next. So not only shaft shoulder create a stress concentration, to add to that, there is this fluctuating effect most of the time, because a shaft usually rotates, right? So whatever bending you are under is gonna be rotating and therefore cycling. Ya kan? Jadi kalau yang tadi kita ngomong nih, yang tadi kita lakukan mana? Exercise ya. Ya, shaft ini kan kena load dari sini, lalu reactionnya di sini sama di sini. Shaftnya bending kayak gini kan? But ini kan kita cuma lihat a snapshot. The next thing happens when the shaft rotates adalah yang tadinya titik, yang tadinya compression jadi tension dan sebaliknya. And this creates the fluctuating stress effect, which we will do next. Jelas ya soal fluctuating stresses. So shaft are typically you have a bending cyclic stress. In spring, you have torsional cyclic stress. Nanti when we get to spring, it'll be clear, right? Connecting rods, you have axial cyclic stress. Jadi, kalau misalnya engines, remember, if this is your crankshaft, lalu engine ini, pistonnya naik turun kan? In combustion. This connecting rod, this is called a connecting rod. It is under compression and tension. That's also cyclic stresses. So failure occurs after many stress cycles and there is no visible warning in advance of failure. Kalau static failure, biasanya dia ada yielding dulu, baru dia patah. Kalau fluctuating stresses, they just suddenly fail. Putus tiba-tiba. Now, in shaft, misalnya ini motor ya, it spins a shaft, misalnya ada gear, lalu dia supported by bearings. Oke, gear ini ada load ke sini, and then seperti biasa lah, bending load. The bending load, because this shaft rotates, the bending load, tadi kita udah ngomong ya, bending loadnya jadinya bolak-balik, ya kan? It's cycling. So the bending is often cyclic, but the torsion is often static. The torsion, puntirannya dari motor, is usually static. Kan motornya kagak puter kanan, puter kiri, puter kanan, puter kiri gitu ya, jarang ya. You know, except in case like maybe like a wiper mobil. Jadi the shaft that turns your windshield wiper in your car itu kan clockwise, counterclockwise, clockwise, counterclockwise. But that's a special case. Most of the time, your shaft just turns in one direction. For example, in a pump or in conveyor belts, most of the time it just turns in one direction. So the torsion is most of the time static, not cyclic. So the way this influence our formula, this is called the von Mises stress. And again, because we skip some of this theoretical foundation, just take it as it is. The alternating stress is sigma A, and the mean stress is sigma M. Now, sigma M and sigma A goes like this. So if this is the chart of the stress, and it's fluctuating like this, sigma M is the mean, the average. Sigma A is the alternating stress. Naik turunnya berapa? Oke, so kalau ini kita fluctuate misalnya di sini 15, di sini let's say 40, nggak bisa ya, di sini 20 lah, 20, di sini 10. Berarti the mean stress is 15 MPa, the alternating stress is 5 MPa. Ya. Jadi 15 plus minus 5. So the alternating stress is governed by this equation on the top. The mean is governed by this second equation down below. They're basically the same equation. Yang beda cuma apanya? Cuma subscriptnya doang nih. Ada A, ada M. So MA, MM, TA, and TM, they each refer to the moment and torsion. In a typical shaft, there is the moment and there is the torsion, right? So MA is the, let me change color. MA is the alternating moment. MM is the mean moment. Jadi sama ya, gambarannya seperti ini. Fluctuating, ada mean-nya, ada alternating-nya ya. TA is the alternating torsion. TM is the alternating, the mean or static torsion. Now, we said before that in most cases, bending is cyclic and torsion is static, right? Therefore, the good news is that most of the time, moment is only alternating and torsion is usually static. Ya, bending is often alternating. Karena kan tadi, if this rod or this shaft is bent this way, remember, waktu ini kan di atas apa? Tension. And down below is compression, right? So we have a situation where you go from plus to minus, minus to plus, plus to minus, minus to plus. Average-nya berapa? No.
0.
Ya, that's why MM the mean moment is 0. Dan torsion karena dia muter konstan, pilin ya, puntirnya, torsionnya, gitu-gitu aja. Alternatingnya 0. Nice, right? So TA and MM is often 0. Therefore, you are now reduced to the alternating stress controlled by the MA. The mean stress is controlled by TM, the mean torsion. Torsional stress is usually steady. This will be useful in determining your shaft diameter. Okay, you will not use this to calculate your moment, but instead, knowing the moment, you need to size your shaft, right? So this will influence your diameter selection. To take it further, we need to calculate the safety factor. Now, safety factor is a pretty simple concept that will be repeated over and over in this course. Factor of safety is basically what is your capacity compared to your demand. Jadi kalau misalnya lift saya, elevator di Prominence Tower, bisa 10 orang. Saya bilangnya gitu ya. So, the elevator capacity is 10 people. Assuming satu orang, let's say 80 kilograms, 10 people kali 80 kilogram, that's 800 kilogram. But my actual elevator capacity is 5,000 kilogram. So what is my factor of safety? 8,000 lah, 8,000 kilogram, easy, right? So if my capacity is 8,000 kilogram, therefore my factor of safety is my actual capacity. I have it able to do 8,000, but I say, no, only 10 people is allowed in the elevator. Why? Because I know you guys, college student, will jump up and down, especially if you get a bad grade in your exam, atau baru ditolak cewek, atau baru dapat pacar, whatever it is, right? People will jump up and down. And so I have to have a factor of safety, right? This factor of safety is N, and I have my alternating stress compared with my endurance strength. This is also something I skipped from the previous week because otherwise we won't have enough time. And we have our mean stress compared with the ultimate strength of the material. Okay? So these are material properties, right? What is my material capable of? These are my shaft stresses. And this formula will give me the factor of safety. Tapi konsep factor of safety-nya jelas ya. It's quite simple. It's what you are capable of divided by what you are able to carry, what you claim to be able to carry. Okay? So we will do this on an exercise next. Example 7.1. So let's take a quick break. Be back. How about now?
Sekarang udah Sir.
Okay, good. So we're gonna do a shaft analysis, shaft design. And hopefully what I just spoke about, the sequence of solution, will become clear as we go through the example. Okay. So here we have a machined shaft shoulder with a smaller diameter and a larger diameter. Okay, so right, so let's say we have a shaft here, right? We have the small diameter D and the big diameter D. All right, this is 28 and 42 millimeters. Each one of these have to be calculated later in meters. Yeah, the radius, even though I don't show it here, the fillet radius R is 2.8 millimeters. So we see the ratio R over D about 0.1. Looks good. Yeah. The bending moment. So this is under bending moment 142.4, and under a torsion, draw it with different color here. Okay, torsion 124.3 Newton meter. Okay, this is bending moment. Now, remember, bending moment itu mengakibatkan stres yang mana? Static atau fluctuating? Which one is it?
Fluctuating.
Fluctuating ya. Moment, tension, compression. Kalau torsion, ya udah gitu-gitu aja. Oke? Okay? So, steady torsion. Dikasih tahu juga kan? So, this is really MA and TM. MM and TA is 0. These are some material properties given. SUT is the ultimate strength, and SE is called the endurance limit. The endurance limit is kind of related to this fluctuating stress. Okay, this is related to kind of a fatigue analysis. Ultimate strength is usually used for static analysis. Okay, so you are given both because you will use both. So with this dimension, it is said, determine the fatigue factor of safety of the design using the criteria that we are already given. Okay, so before we do any stress analysis, then we have to determine those the case, right? The stress concentration at these shaft shoulders. So first is the bending moment. Okay, notice this guy. Lihat gambarnya ya. Itu artinya apa? It's bending moment. Karena ada tabelnya lagi, ada plotnya lagi untuk torsion, beda ya. Nih, ntar ada nih. Ini torsion, lihat. Oke, chartnya beda ya. So, jangan ketukar. Lihat gambarnya. So, first we do it for the bending moment. So, for the bending moment, masih laser pointer. We first calculate R over D. Mohon apa ya? So, R over D is tadi berapa? 2,8 dibagi 28, 0,1. Big D over small d 42 dibagi 28. So using these numbers, then we look at the plot. Lihat garis-garisnya dulu. D over D equals 3, D over D equals 1.5. There we are. Okay? R over D, 0.1. And therefore, my KT is approximately 1.68. This is for the bending, yeah? This is for the bending. Next, we do the Q. This is also for the bending. Not sensitivity. Look at the radius on the top because our radius is in millimeters. Yang ini inches ya. Jadi jangan pakai yang bawah. Use the top. Radius in millimeters. Our radius is 2.8. 2.8 millimeters. SUT, we were given 735. So approximately here, right? 0.735 GPA. Therefore, Q is approximately 0.85. Any questions so far on looking up these plots?
Sir, I
Yeah.
don't understand how you get 0.85.
It's just looking up the chart. Look at the red dot that I mark.
Okay.
Terus tarik ke kiri. So, nah kayak gitu.
Okay.
Ya.
Jadi dilihat dari
Oh.
SUT-nya ya tadi ya, Sir.
Jadi SUT-nya itu kamu memilih garisnya.
Oh, oke. Jadi
Ya,
kalau
garisnya
misalnya
kan ada
ini,
banyak nih.
Iya.
Gitu kan. And then R-nya itu vertikalnya.
Jadi, Sir, kalau misalnya kayak gitu, kita lihat dari yang notch radiusnya, habis itu kita tarik ke bawah, kita lihat titik mana yang kena gitu atau gimana?
Iya. Ininya gampang ya. 2,8 ya. Lalu yang lebih susah nih garis-garis ini loh. Garis ini kan garis 1,4. Ini nih, garis ini kan garis 1,4 GPA. This is 1,0 GPA. Ini 0,7 GPA. Nah, kita punya SUT berapa? 0,735 kan? Ya, kira-kira di sini garisnya gitu. Right?
Okay.
So, we have a multi-dimensional plot here. Ini juga sama yang tadi. Ini kan D per D 3. Ini 1,5. Kalau D per D 2 gimana? Ya di sini kira-kira kan. Nah, kayak gitu kan kira-kira garisnya. Any other question? So, belum selesai karena kita perlu KF ya. Jadi, kalau saya coba bikin chart ya. We're still doing this for the bending part, okay? We're not even doing this for the torsion. Oke, bending tadi kita udah bilang MA 142,4 MM 0 ya. Mean 0, dia alternating. Torsion PA 0, PM is 124.3. Stress concentration, we did KP 1.68, we did Q 0.85. So the KF is 1 plus Q times KP minus 1. So it's 1 plus 0.85, 1.68 minus 1. So 1.58 is the fatigue stress concentration factor. Okay, so KT is the stress concentration factor. KF is the fatigue stress concentration factor. Ya, jadi we include this fatigue effect. Now, we need to do this for torsion as well. So let's look up the chart. Again, this is a different chart. Look at the T on the legend. Also notice that here it's called KTS, shear. It stands for KT shear. Our D over D was what? Tadi 1.5 ya. Man, this stylus. R over D is berapa tadi? 0.1. All right. D over D is 1.5. This is D over D Ini 1.13 ya. So 1.5 ya disitulah tengah-tengah ya. R over D is 1. So KTS is approximately 1.42. Any questions on looking this up? Ya, 1.42 karena dari textbook. Kalau nggak mah, I would estimate like, 1.45 maybe ya. One more, Q shear. Beda ya. This is for torsion, Q shear. Again, use the top because we are doing this in millimeters, not in inches. So here is 2.8. Okay. And again, we are at 0.735. Jadi line-nya kira-kira di situ tuh ya. And we are steel ya, not aluminum alloy. If it's aluminum alloy, use the dotted line. So here, 2.8. So Q shear is approximately 0,92. We combine it here, okay? We did KTS 1.42, Q shear 0.92. So KFS, S stands for torsional shear, 1 plus QS times KTS minus 1. So 1 plus 0.92, 1.42 minus 1, 1.39. So we obtain KFS for torsion. Any questions so far? This all comes into the big equation soon. All right. Here are the big equation, the shaft equation for alternating stress and mean stress. Again, the good news is which part of this is 0 on the top equation?
Torsion, Pak.
All right, PA is 0. So that all goes to 0. Therefore, we have 32. KF, again, this is F from the bending. KFS for torsion, yeah. And the D here is the small d. You notice that the small d is the one that is governing the shaft design here, not the big D, because obviously it's a bigger stress. So that's the alternating stress. On the bottom here, which term is 0?
MM, Pak.
Mm. So that goes, we have 3 times, oh, I'm sorry, that's square root of 3 because we have the, ada akarnya ya. Kalau ini nggak ada 3-nya, jadi ininya langsung coret. 2 sama pangkat setengahnya ya. Di sini 2 sama pangkat setengahnya juga coret, tapi 3-nya kena pangkat setengah ya. So it's akar 3. 16 KFS Handwriting is a bit tough digitally here, so bear with me. Cannot wait until we get back to campus, man. I love the whiteboard. 69.4. Okay, so this is the mean, and above that is the alternating stress. Which one of these will govern failure? Well, it's both. So here, 1 over n. N means the factor of safety. Yeah. 104.4 divided by the endurance limit. You are given that in a problem. What is it? 205. And 69.4 divided by 735 is the ultimate strength. So I solve this, n is equal to 1.65. So what does this mean? What does 1.65 means? Can anybody tell me how to read that number in English? What does that mean?
Itu safety factor kan, Pak?
Right? So what does that mean? That means
Ya, kita bisa taruh force-nya itu maksimal shear stress-nya itu di 1,65 dari force maksimal yang kita taruh.
ya. Jadi the actual capacity of the shaft is 1.65 times the load that is given here. Right? So dengan loading sekarang ini masih aman. You still have 65% extra strength. Gitulah boleh dibilang ya. So it's important for you to understand this concept, because otherwise, if I ask you back, calculate for me the diameter, the minimum diameter for this load. Kalau saya tanya balik, calculate for me the minimum diameter of the shaft that will sustain this load. How would you do it?
Dari safety factor dulu, Pak. Kita
Safety
cari
factor-nya berapa?
ya, safety factor-nya kan dari 205 sama 735 kan, SI sama SUT-nya kan, Pak. Cari itunya, Pak, stresnya, Pak.
Stresnya kan juga tergantung diameternya.
Enggak,
Jadi-
Pak, stresnya kita substitute masuk dulu angka apapun, Pak, yang dari required safety, supaya bisa produce required safety factor-nya, Pak.
Required safety factor-nya berapa? Kalau misalnya saya bertanya minimum. Minimum to survive the load, artinya kan it's marginally surviving ya.
Iya, ya.
Jadi
Satu,
safety
Pak,
factor-nya
safety
adalah
factor-nya.
1. Right? Konsepnya begitu ya. Makanya saya bilang tadi it's important for you to understand the concept of safety factor, not just the formula. Because the understanding is that kalau safety factor kamu 1, artinya dengan beban itu, iya dia kuat. Tapi kuatnya tuh pas-pasan banget gitu kan. Gitu ya. So, if you are calculating diameters instead of safety factor, then it's the opposite, right? Factor of safety-nya 1, lalu kamu nggak tahu diameternya. Nah, memang diameter juga mempengaruhi KF sama KFS. Tapi itu sesuatu yang masih bisa di-estimate, Pak. Ya. But the point is here, the diameter is now the unknown, and you put in factor of safety of 1. Okay? Now, you actually need to do one more thing. We need to do a checking for static yield. check for static failure. Karena yang kita lakukan tadi adalah fatigue failure, ya, dengan many cycles, right? Check for static failure is because the maximum is the mean plus the alternating. Remember, the fluctuating stress, this is mean plus minus sigma A, right? So the maximum possible is actually sigma M plus sigma A. The reason we check for static failure adalah gini, what if before it even fluctuate and fail over a long time, it fails on the first cycle? That's called static failure, right? Static failure here is 104.4 plus 69.4. Therefore, absolute maximum stress is 173.8 MPa. Therefore, the factor of safety for static is you compare the yield strength with the max. Okay? Yield strength is 574. Again, this is probably given in the problem, but maybe I didn't put it in my slide. Yeah, again, you can check this on problem example 7-1 in Shigley's textbook if you have it. But if not, consider the 574 as a given number. Okay? So 3.3. Therefore, looking at this number compared to the fatigue static failure, fatigue factor of safety, it is safer in the static condition than in the fatigue condition, right? Which is expected, right? The fatigue factor of safety is 1.65. All right? Any question so far? So I would like to give you kind of the big picture of what we did, right? Shaft design. Remember, there is two kinds of loading: the bending and the torsion. Shaft loads are composed of bending and torsion. Now, bending is typically cyclic, and torsion is typically steady. Therefore, you only have alternating, and MM is 0. Steady means your alternating is 0, and TM is something, right? We will feed this to the von Mises equation. Sorry, I'll just write it up here. Okay, this will create the alternating stress, and this will create the mean stress. However, don't forget that we have stress concentration. We have bending stress concentration. We have torsion stress concentration. So first we find KT, Q, and then this combined become KF. Again, we have KTS, QS combined into KFS. All right. So KFS feeds to the torsion part. This feeds to the alternating moment. Okay. And finally, this alternating end moment, mean, they combine to find the factor of safety. And factor of safety, you check for fatigue and you check for static failure. Okay? That's kind of the big picture or summary of the procedure in doing shaft design. Any questions? Okay, if there is no question, I think that should be enough for shaft design and analysis. We will continue to rolling contact bearings next time. Okay, if there is no questions, let's do the post quiz, post test.